We're going to go ahead and do a few more implicit differentiation examples with the goal of being able to learn related rates, which is an application of implicit differentiation. So in this first problem, we're going to suppose that x and y are both functions of time. So before we were thinking of y as a function of x, now we're thinking of x as a function of time and y also as a function of time. So we could write maybe like x of t and y of t instead of just x and y to remind ourselves that these are functions of another variable. And these are related via this equation. Sorry, it goes on to two lines. And then I've been given some other information here. And I want to find something about dx dt. Okay. The first thing before we worry about what all of this information says is we're going to need to take the derivative of our original expression. And we're going to take our derivative with respect to time because all of our derivatives here are of the form dt. So we're going to take the derivative with respect to time. So I'm going to differentiate. This is implicit differentiation, both sides of the equation with respect to time. So I'm going to take the derivative of that side with respect to time and then the derivative of the other side with respect to time. Okay. So here's the trick that when I'm differentiating here, whenever I take the derivative of either an x or a y, I'm going to have to use the chain rule, just like we did when we were talking about implicit differentiation, because this is implicit differentiation just with another variable. So let's do the right-hand side first. So when I take the derivative of the y piece, it's going to behave like it did with implicit differentiation. We take the derivative like we normally would, 9y squared, but then we have to multiply by the derivative of the y. I'm going to write that as a dy dt here to indicate the fact that it's dependent on time, not on x. Okay. Now we're going to take the derivative of this piece using the product rule. So I can leave the 2x alone. The derivative of y is dy dt. Now I have to take the derivative of the 2x. X now is a function of time. So when I take the derivative of x, it's going to be dx dt. This is where this is a little different than what we did last time because now x is a function of time as well. So the derivative of 2x is going to be dx dt. Y stays alone. The derivative of 4 is just 0. Okay, and so now on the other side of the equation, remember x squared, x is a function of time. So I'm going to have to use the chain rule to take the derivative of x squared, also the chain rule to take the derivative of cosine of x squared. So the derivative of the cosine of x squared, the outside function is cosine, the inside function is x squared. So I'm going to end up with negative sine squared, or negative sine of x squared times the derivative of x squared, which is 2x dx dt. If you needed help figuring out how I did this piece here, we're thinking of my outside function being cosine of x, and its derivative is negative sine of x. Forget the negative. My inside function is x squared. Its derivative, because x is a function of time, is 2x dx dt. Remember, we take the derivative normally, and then we multiply by the derivative of the x, or by the derivative of the piece. And so then we put these back together by plugging the x squared into the derivative and then multiplying by the derivative of the inside. Okay. Okay, so now at this point, this looks like a pain to solve for anything because we have dx dt and dy dt in here. So at this point, this is where we're going to plug in the information that they've given us, okay? So they tell us at time 1, this information is true. T never appears in my equation here, so I'm not going to plug t equals 1 in anywhere, but it's just that we're being consistent that everything we're asking about is at the same point in time, okay? So they've told us that x is equal to 0, so let's replace all the x's with a 0. When I do that, this whole term will go away because I'm going to have 0 times something. And this term is also going to have 0 times something, so that whole term will be 0 as well. So we're going to have 0 on this side of the equation. We know that y is equal to 1, so we can replace all of our y's by a 1. So this is going to give me 9 times dy dt, which they told me is 2. So I'm going to have 9 times 2 here. And then I'm going to have 2. dx dt is the thing we're trying to find, so we'll leave that alone. And then y again is 1. Ooh, sorry guys. Times 1. Okay, and now we can solve for dx dt. Notice that once we've plugged in the numbers, life is a lot better. Don't try and solve for dx dt before you plug the numbers in. So we're going to get 18 plus 2 dx dt. And when we solve this, we're going to get dx dt is negative 9. Okay, we don't have any context for this problem, so we don't know what kind of units this would be, or we don't even know what the negative 9 would mean. in related rates problems, this will have more meaning to it because it will be in the context of a word problem. Okay. So we can do another example here. So we can suppose that A and R are both functions of time and that A is pi r squared. That's the area formula for a circle. So essentially what's happening here is we're thinking about a circle that's growing or shrinking with time, and both the radius and the area are changing. Okay. And so we know some information that when r equals 3, dA dt is 2, and we want to find dr dt when r is 3. Okay, so I usually kind of try and classify the information they've given us so we know the things that we know are that r is 3, when r is 3, dA dt is 2, and we want dr dt. Okay, so because we want derivatives and we know things about derivatives, and we have an equation that relates A and R, we're going to take the derivative of this equation with respect to time again. So we're going to differentiate both sides of this equation. So the derivative of A will just be dA dt. A is a function of time, so it's just going to be dA dt. The derivative pi is a constant, so it gets to hang out front. And then the derivative of r squared is 2r times dr dt, again, because r is a function of time. Okay, now we're going to plug in the things we know. Remember, plug in things before you solve. So we know, if we highlight the things that we know that dA dt is 2. So we're going to have a 2 on the side of the equation. We'll keep the pi times 2. We know that r is 3. So we'll replace the 3 here. And then the thing that we're trying to find is dr dt. So we'll leave that alone. Okay. And so now this is all multiplication over here. So we can divide that all over. So we have 2 divided by pi times 2 times 3. 2's will cancel each other out, so we're going to be left with 1 over 3 pi is dr dt. You could get a decimal for that, but I like leaving it like this.